Hi everybody. So what I wanted to do in this video is just to go over my solutions to the first midterm. Now I already posted some solutions to Brew and Learn, to Canvas, but those are kind of the solutions that I would write down if I were taking the exam, right, in the space allotted on the exam. And so I don't explain things in a lot of detail, right? I don't write out my thought process for anything. And I thought it would be useful for me to go over that in a video for you. So let's go ahead and get started on that. Starting with the first problem here. So this problem should look pretty familiar because it's essentially a problem that we did in lecture. If you'll recall, we had this example when we were starting doing calorimetry of ice melting in water. And in that problem, we were trying to find what mass of ice we needed to bring the system to a certain final temperature when it came to thermal equilibrium. Okay. In this case, we have the mass of the ice and the mass of the water, and we're trying to find what their final temperature is. But it's the same setup, so we're just going to use calorimetry. So the heat for the ice and the heat for the water add up to 0. And I just need to write out what these heats are. Now let me start by just writing down some variables here for the mass and the specific heat of the ice and the water. So the mass of the ice is 5 grams. The specific heat of the ice, at least while it's still solid, is 2.1 joules per gram Kelvin. I gave the mass and the specific heat here both in grams, so you didn't have to convert to kilograms. And then for the water, the mass is 100 grams, and the specific heat is 4.19 joules per gram Kelvin. All right, now if we want to write down Q for the water, that is relatively straightforward because all we're doing is we're taking the water and we're bringing it from its initial temperature, which is 20 degrees Celsius or 293 Kelvin, down to whatever the final temperature is. So for the water, we're just going to have M2C2 and then T final minus 293 Kelvin. Okay, we could write this down as a variable, but I'll just leave it as a number. Now for the ice, it's a little more complicated. For the ice, we have 3 steps, right? We have to bring the ice to 0 Celsius, at which point it melts. We need heat to melt it, and then we need heat to bring it up to whatever the final temperature happens to be. Okay, so I'll break those up. I'll call those 3 processes, A, B, and C. A is bringing the ice up to 0, B is melting the ice, and then C is bringing it up to the final temperature. And A and B we can calculate numerically. C we don't know because that depends on the final temperature, which is what we're trying to find. So for A, we just have the mass of the ice, the specific heat of the ice, and then we're going from negative 10 Celsius up to 0, right? So that's going to be a temperature difference of 10 Celsius or 10 Kelvin. Remember, temperature differences are the same in Celsius and in Kelvin. Okay, so we could go ahead and just calculate that right now. Remember, our mass was 5, our specific heat is 2.1, and then temperature of 10, so we get a heat of 105 joules for that step of this process. Then to melt the ice, step B, we have to add the heat of fusion. So we'll take the mass of the ice times the latent heat of fusion. Okay, that was also given. as 333 joules per gram. So I'm just going to take 5 times 333. That gets me 1665 joules. And then finally, we need to heat the ice up from 0 degrees Celsius. Right, the ice is now liquid water. We need to heat it from 0 degrees Celsius up to whatever our final temperature is. So now the ice is melted to liquid water. So we want to use the specific heat for liquid water, which we labeled C2 earlier. Okay, and we're going from 273 Kelvin up to our T final. All right, now I just want to write out, so add everything together and write out my calorimetry equation. So that's going to be, again, Q water plus Q ice is 0. So that's M1, C1, T final, minus 293 for the water, plus QA, plus QB. Okay, we have those as numbers, so I'll just leave them in here as variables, and then plus M2. Sorry, this is 2. The water was 2. M2C2. This is M1C2. T final minus 273 Kelvin. And this all adds up to 0. And now we're just doing algebra to get T final. So what I can do is I can distribute out both of these terms here in parentheses. Okay, that's going to give me M2 C2 T final plus M1 C2 T final, and then minus this stuff. Okay, and then I can move, I'm trying to isolate T final, so everything that doesn't depend on T final, I can move over to the right-hand side, and I'll just end up with, I can factor out the T final on the left here. So I'll get M2C2 plus M1C2 times T final is equal to negative QA minus QB, and then plus this other stuff, right? So plus M2C2 times 293 Kelvin plus M1C2 times 273 Kelvin. If I can squeeze that in there. Here, let me do this. Okay. And then I just divide by this thing in parentheses and I get my T final. So it's the total mass, M1 plus M2 times the specific heat of water. All right, so now I can plug in. I have minus my two heats I calculated earlier. So minus 105, minus 1665, plus M2. Remember, system 2 is the water here, so this is 100 grams times 4.19 times 293, plus M1, which is 5 times 4.19 times 273, and I'm going to take all this, divide by the total mass, right, 100 plus 5, and then times the specific heat of water. Okay. So I end up with this number, 288 Kelvin. All right, and that's my answer for part A. All right, now part B. Part B is a conceptual question about the entropy in this process. And it says, do you expect the total entropy of the ice-water system to increase or decrease in this process? Okay, now the problem tells us that the ice-water, throughout this process, the ice-water system remains isolated from its environment. So right away we know that it's not possible for the entropy of the system to decrease. Okay. That's just the second law of thermodynamics. So, without even really needing to think about anything beyond this, we know that if our two options are increase or decrease, decrease is forbidden, so it's got to be increase. Okay, now that's one way to think about it, and that's a perfectly fine way to answer this question. If we think about it a little bit more in terms of what the actual process taking place here is, well, this is a heat flow, right? It's the spontaneous flow of heat from the water to the ice and the melting of the ice. And that's an irreversible process, right? A spontaneous heat flow is always irreversible. And in an irreversible process, the entropy goes up, okay? So by that logic also, we can conclude that the entropy has to increase. All right, so either way we think about it, we end up with this conclusion, right? The entropy is going to increase. Okay, then part C is asking us, now let's actually calculate what the entropy change is, and we want to show that it agrees with the answer we got in B, right? We want to show that the entropy increases. In this problem, when I was preparing this problem, I found that I was getting different answers depending on how I plugged in my final temperature here, or how I rounded my final temperature. So the answer was very, very sensitive to rounding, okay? It shouldn't matter what temperature, it shouldn't matter how I round the final temperature for calculating the sign, but the numerical value of delta S will be different depending on the temperature I use. So that's why I only asked you to get the sign here, okay? All right, so we'll do the same thing that we did in part A, in the sense that we're going to break this up into, essentially four different steps here. 3 steps for the ice and 1 step for the water. All right, so our total entropy change, that's delta S for the ice plus delta S for the water. And again, for the water, it's easy because all we're doing is we are cooling the water down from 20 degrees Celsius to our final temperature of 288. Right, so we're just going to use our formula here. So this is M2C2 natural log of T final divided by T initial. Okay, this is our entropy change formula for a temperature change for heating or cooling. And I can plug in my final and initial temperatures here. Okay, and so I can get some number for this. In fact, let's go ahead and just calculate it now. Okay, so I get this number, negative 7.2 joules per Kelvin. It should make sense that it's negative because the water is cooling down. All right, now for the ice, I'm going to have 3 separate entropy changes corresponding to the processes A, B, and C that we mentioned earlier. All right, so A is going to be heating the ice up to 0 Celsius, or 273 Kelvin. So my T final here is 273, and my T initial was negative 10 Celsius, which is 263 Kelvin. Okay, the units of Kelvin cancel out inside the natural logarithm, so I don't need to worry about that. For step B is an isothermal process because it's the melting of the ice at 0 Celsius. Right, so for B, in fact, let me move this so I have more room. So for B, I'm going to use my Q over T formula, and my T here is 273 Kelvin, right, 0 Celsius. And QB we calculated earlier. And then finally, I need to heat the ice up, the now melted ice, heat it up to my final temperature of 288. And this is going to take place while the ice is liquid water, so again, I need to use the specific heat of liquid water. Okay. And I know everything here, so I'm just plugging in. Right? So I have this. Okay, so 5 times 2.1 times this logarithm plus my QB, right? That was the 1665 we calculated earlier, divided by my temperature, and then 5 times 4.19 times this logarithm. Okay. And everything here is positive because it all involves energy transfer into the ice, heat flow into the ice. Okay, so I add it all together and I get this positive number, 7.6 joules per Kelvin. And as we expected, when I calculate the total, right, by just adding these two together, so 7.61 minus 7.212, I get this number, right? About 0.4 joules per Kelvin. All right, and that's our answer, right? Again, the specific number that you get is going to depend on how you round the temperature, but we did get that it's positive. So since the entropy is positive, we find, or since delta S is positive, we find that the entropy increases as we expected from part B. All right, now let me move on to the second problem. The second problem should also be pretty familiar because this was a problem, basically a problem on your homework. I don't think it had the buoyant force part, but the rest of it, I think, was just a homework problem. I sort of forgot that as I was writing the problem, but I don't think anybody's going to be too upset about that. So the problem is we have a bubble of gas that we're modeling as an ideal gas. It starts at the bottom of a lake, and then it's going to, because of the buoyant force, it's going to ascend to the top of the lake. Okay? So we're given the temperature at the bottom of the lake. We're given the temperature at the top of the lake. We're assuming that the pressure at the top of the lake is atmospheric pressure, because the surface of the lake is, of course, open to the atmosphere. And the pressure at the bottom of the lake we can calculate using our hydrostatic pressure formula. So the first step of the problem, part A, is just to calculate how much gas, what amount of gas in moles the bubble contains. And we can just do that by plugging into the ideal gas law. Okay, so I'm going to do PV equals nRT. So N is PV over RT. Okay, now I'm given T, right? T at the bottom of the lake. Let me draw a picture to get myself organized here. Okay. So here's our bubble down here. We're at 10 meters below the surface. Our temperature down here was 10 Celsius, so 283 Kelvin. Right? And of course we know R. The volume we can calculate from the given diameter of the bubble, right? So I gave you the formula here for the volume of a sphere in terms of the diameter, so we can just plug into that. I've got T is 283 Kelvin, V, okay, my diameter is 1 centimeter, my volume is pi over 6 d cubed, so let's calculate that. So about 5.24 times 10 to the minus 7 cubic meters. And for the pressure, again, we're assuming atmospheric pressure at the top here. So my pressure at the bottom I can get using the hydrostatic pressure formula. Okay, my density, just the density of water, 1,000 kilograms per cubic meter. And the atmospheric pressure, that's 1.01 times 10 to the 5 Pascal. And so I can just plug into that to get the pressure. So I get 199,000 Pascal, 199,000. And now I have everything. I can just plug in to the ideal gas law. So again, it's P times V over R times T. So I get this number, 4.23 times 10 to the minus 6 moles. Okay, that's my answer for that part. Part B is asking us, okay, so now the bubble is going to move up. It's going to ascend to the top of the lake. And we want to calculate, now that it's up here, what's the new diameter? Right, so the volume is going to change because both the pressure and the temperature change, right? We have a new temperature up here, which is 293 Kelvin. Our pressure now is just atmospheric pressure. And again, we can use the ideal gas law. So we have the number of moles. We could just plug into that, or we could do P initial, V initial over T initial equals the same thing, but final. Okay, either one works. So our V final now is going to be T final over T initial times P initial over P final times V initial. And everything here I know, so I'm just plugging in. Okay. So 293 over 283. the ratio of the pressures, and then times the initial volume. Okay, so I get this number, 1.07 times 10 to the minus 6 cubic meters. And I'm looking for the diameter here. So I can just use my volume formula, rearrange that, and get the diameter. Right, so V is pi over 6d cubed, which means d is going to be the cube root of 6v over pi. Right, so I get 1.27 centimeters. All right, that's my answer for part B. And then finally, part C is, now that our bubble is at the top, so in this picture here, it's totally submerged still, but it's at the top and it has this volume, this diameter. Right, what's the buoyant force on it? And this is really just plugging in to our buoyant force formula. So it's the density of the fluid, which is the water in this case, times the volume of the bubble, and then times G. So that's just 1,000 for the density times this volume times G. Okay, so I get 0.0105 newtons. And that's it. All right, so thank you, everybody. I hope this was helpful. Let me know. I think I'm going to post this to YouTube, so you should be able to post comments. If you have any feedback on this, put it in the comments. I think I'm going to continue trying to post videos. My next video idea is to record my solutions, record myself explaining my solutions to the past midterms, which again, I have solutions posted, but they're not super detailed, so I want to go through them in detail like I'm doing here. If you have any other suggestions for other videos you'd like to see from me, let me know. And again, if you have any feedback on this, other things you'd like to see if I do similar solution videos in the future, please let me know. All right, thank you, everybody, and I'll see you later.